Calisto Zuzarte. I'm at the IBM Toronto lab in the Db2 development organization. I kind of look after all the warehouse query optimization and performance. John Honeybrook is there. He's also my colleague involved in the same thing. You know, he's been involved in HTAP and other stuff, but also involved in query optimization and performance. This session, I'm going to focus on SQL. It's more of an application query writing session. I have given this session in IDUG in EMEA, so you'll find the same slides there if you have access to that. So it's not changed too much from that. So the background is after looking at many of these POCs and customer issues that we've seen over the last 3 or 4 years based on our column engine. There have been many cases where we've not done as well as we would have liked to do. And of course, most of our development is driven by what we see in the field, and a lot of this are things that we will eventually put inside into Db2. And for the time being, if you see issues with query performance in a warehouse environment, typically very large tables, large number of joins, scenarios which are typical of a warehouse environment, there might be opportunities to improve performance based on rewriting the SQL. Okay, so what I'll do is I'll go through a few scenarios, typically ones which involve outer joins, aggregations, correlated subqueries, or predicates. So I'll go through some scenarios, and the way I'll do this is by showing you 2 slides for each scenario. The first slide, I'll show you the typical SQL that might be written, and I'll show you how to rewrite it to get better performance. I'll use the color scheme where red shows a problematic area, and green is how we get rid of that problem. On the second slide, for that scenario, I'll show you a diagram. It typically reflects the structure of the plan that the optimizer chooses. And again, the red will highlight where the problem is. The green shows you where the operations are not a problem. And I accompany that with some numbers. And the numbers are based on, they're just fabricated numbers, but they kind of highlight what the problem is. Okay, so let's start with the first scenario back again. So this is one with outer joins. And a typical example, and I've shown, if you see these, they look like cryptic queries with T1 and C1 as table names and column names. But I tried to come up with some realistic SQL and found that it took up too much of space, real estate on the slide. So I kind of compressed it. The idea is just to get the gist of the rewrite. You can always go to the slides again to look at the actual transformation in detail. So here we have a join, 2 left outer joins. So T1, left outer join T2, and then left outer join T3, and then some inner joins. And you can see here, it's a typical query. There is a filtering predicate on one of the inner joins, which is on T4. So typically that's a filtering join. If we come up with the plan exactly as we saw here, as we see here, where the filtering join is done after the left outer joins, that kind of tells you that that's not a very good plan to get good performance with. And on the right-hand side, you can see that we've reordered and pushed the inner joins before the left outer joins. And that's kind of the recommendation that I would give you. If you have a mix of inner joins and outer joins, unless the inner join is an expanding join, try to put the inner joins first and leave the left outer joins at the end of the query. So that's a recommendation. We do this inside of Db2. It's a cost-based rewrite, and often what happens is either the statistics are not up to date, or we don't have the right column group statistics, the right information to make that decision to push the inner joins before the outer joins. In that case, we'll structure the plan as it was written. So you can see here, we have 10 million rows coming from T1. The left outer join never reduces a join. The output of the left outer join is never smaller than the row preserving side of the join. So a left outer join typically says, match all the rows from T1, from T2, which match the values in T1 in the join column. If there is no match, just pad it with nulls and send it out. So you'll never find this number greater than the row preserving side of the left outer join. So you can see that we've got two big joins here, 10 million here. And then the filtering join on T4, because of that one filtering predicate, reduces it to 5,000 rows. If we reorder it so that we do the filtering join first, this might be just a lookup join, so it doesn't increase the size here. So we have 5,000, 5,000, and you can see the two left outer joins and compare it with the one on the left-hand side. You can see that it's so much easier to do that join because it has fewer rows. So the takeaway here, do your filtering inner joins or filtering or lookup inner joins before your outer joins. The second scenario, what if your left outer join, here you see a simple T1 left outer join T2. What if your left outer join, the null producing side of that join is a very big table? If you look at the diagram on the next page, you can see that this is a left outer join, but it's shown as a right outer join here. This is a very big table, a 100 million row table. This is a DPF environment, so you can see some table queues, which are the mechanism we use to move data from one partition to another. And you can see that by the time we do the outer join, we have 100 million rows moved across the DPF, the MPP complex, and then the outer join done. The reason why we do a right outer join here is because we always, if this is a hash join, we always want the smaller table, or typically we want the smaller table to be the hash table so that we don't use too much memory. But this is an expensive operation here. So the way to solve this is we use what we call a semi-join. So if the row preserving side of the outer join is a small set of rows, we take the distinct values of the join column, just the join column, we don't need anything else. We take the distinct value from T1, applying the local predicate which was in the where clause, and join it to T2. Inner joins are a little more flexible when it comes to doing these joins, because we can do, if you see the diagram on the next page, you can see that we don't have to move the rows, or actually in this case we do, but there's a TQ missing here. But we don't have to have the complete set of the null producing site to do the join. The reason why we have a redirected join here, TQs on both sides, is because we need either a collocated join to do the left outer join, or we need to broadcast the entire null producing site, which is impossible in this case because it's a very huge table. So essentially doing the semi-join allows us to reduce the size of the null producing site. So we flow the rows from here after this joint, and now we have much less data to move around the MPP complex. So this is a semi-join. It's something that we have inside the product, but it's not active in all situations. But this is something that you can also use to reduce a very large null producing side of an outer join. Okay. The next scenario is aggregation. In this case, I'm joining T1 to a subquery. I've shown the subquery in red because it could be a very large subquery. These are two tables which are joined within the subquery, and we are computing some aggregation. And then we are doing the join of T1 and the result of this subquery on this join column. What we want to do here is very similar to the previous scenario with outer join, where we are using a semi-join to reduce the size of this subquery. So we can take the distinct values of the join column of T1, apply whatever local predicates are there, and reduce the size of what we are computing as the aggregation. So pictorially, this is what it looks like. In the previous case, we had the subquery, which is this. We joined the two tables. They are very big tables. We do the join and then aggregate on a very large stream here. So you can see 100 million rows being aggregated to 5 million rows. With the rewritten query, what we do is we do the semi-join of T1, do the reduction on T2. You have a smaller join here with T3. And you can see that what you're aggregating is only a subset of the rows that we were aggregating previously. So this is another use of semi-join. So it's not a new technique. It's been around for a long time. It was typically used in distributed systems to start with, where you did these semi-joins in a distributed manner so that you move less data to do the final join. The next one focuses on aggregation. This time, we have a bunch of tables that are being joined. So T1 joined to T2, T3, T4, T5. So it's a 5-table join. You have some local predicates on T2 and T3. And there are two aspects in this scenario. One is the result of the join could be fairly large. You could have some expanding joins in T4 and T5. And also you could have a bunch of wide columns that are picked up from the dimension tables as part of the join that also feed into this aggregation. So you have a large number of rows to aggregate. As well, you have a large number of columns in the payload that are part of this aggregation. So the ones in red are the wide columns. So what we do here is what we call eager aggregation. Again, this technology is not new. It's been around for at least 25 years. We had a student come in from University of Waterloo who did some research and came up with a paper as well based on what he observed in Db2. So it's been around, except that we haven't aggressively pursued it in the product as a automatic rewrite. It has to be, it's tricky because it has to be cost-based. So the idea here is to do a partial aggregation before some of the joins. So we do it after the filtering joins, before any expanding joins. Let me show you the picture because it's easier to follow that. We have a 100 million row fact table here. We do the join to these filtering joins to these dimension tables, T2 and T3. And here's one where we pick up some wide columns. And here's an expanding join where we increase the stream to 200 million. For example, you do a join on the month of the date column in the date dimension. And you can imagine that whatever row that comes from the fact table is going to be increased by a factor of 30 or 31 or 28 in February. But you could have an expanding join there. And we have a very large number of rows to aggregate, as well as very wide columns involved. So what we do is we do this group by. Instead of taking all the columns that are needed from here as part of the group by columns, we just take the join column and replace those columns with the join column and do the aggregation here. So you can imagine we don't have all those wide columns that come from T4, and we're not dealing with the expansion related to T5. So we do the aggregation on a much smaller set of rows here. So we reduce the stream somewhat. And then when we are doing this join, we pick up the wide columns, and we do expand with this join, but you can see that the numbers are much smaller, 500,000 versus 10 million, 10 million here versus 200 million. And then we do the final aggregation, but it's on a smaller set of rows, and the final aggregation does have the wide columns, but it's on a much smaller set of rows. Okay, so this is another similar kind of scenario. This is with distinct. Now, in this case, we have T1 joined to T2, T3, but we also have it joined to some select distinct queries. There could be a view which has a select distinct in it. So you could have a view with select distinct of some columns there. And in this case, I have two of those subqueries that we are joining. One of the things that we had, and particularly with the row engine, was we would, instead of removing the duplicates right away, we would say, oh, there's going to be a sort somewhere soon, maybe for a merge join, or for an ordered nested loop join, or for the group by, or for the final order by. Let's remove the duplicates when we are doing a sort for some other purpose. In the column engine, first of all, we don't have merge join. So there's not going to be any sort there. We don't see an ordered nested loop join either, because the column store is predominantly hash join based. Aggregation, we don't do sort based aggregation in column store. So there are no opportunities to piggyback duplicate removal with some sort for merge join, nested loop join, or aggregation. So what I would recommend here for the time being is to change this distinct subquery into a group by. So you have the same columns. remove the distinct from here and add this group by column. It's semantically identical to what is there in the distinct. In DB2, it's just that when we see a group by, we always do the aggregation. So we don't say, okay, there's going to be a sort later on, let's combine it with something else. We don't do that. We just remove the duplicate. So this is an easy way to force the duplicate removal on a smaller table rather than doing the join and waiting for, after the join to a fact table, it could be a very large stream, and we don't want to do the duplicate removal on a large stream. If you have views with select distinct in them, change them to a group by, and you will have the early duplicate removal done.
I got a question.
Sure.
I don't quite get that. What's going on when you optimize the group by the distinct so that you got the same number or the same exact result set in those
That's right.
expressions? So what's it doing with the group by different than the distinct? I'm not missing here.
So in our code, it's just an implementation thing. In DB2, when we see a group by, we always just respect that and remove the duplicates. There is no aggregation function here. It's just a duplicate removal.
But you do the same with distinct.
We could do the same with distinct, but we don't because of the code that we took from the row engine as part of the optimization strategy for the column engine as well. In the row engine, we didn't see the need to remove duplicates very early, very aggressively, just because we always had some other opportunity, close by to remove duplicates. It's just an implementation thing. Okay. So these are projects that we are looking at in the context of column store, and things will change in the future, but this is what I would recommend if you do see a problem with too many duplicates going through the plan. So here's the thing. T4 and T5 are the things which had distinct, but we didn't remove the duplicates here. So they expanded the stream, and then we did the sort for the order by on a much larger stream. So here you can see T4 and T5, we force the group by, we remove the duplicates, and we don't expand the stream here. And you can see that the order by or whatever aggregation was done later is on a smaller stream. Okay. So this is aggregation distinct. We are doing a count distinct. We want to find the number of distinct values in C1 and group by C0. In the row engine, we did a sort-based aggregation. So we sorted it on C0, C1, and then for each value of C0, we computed how many distinct values are there in C1. Now, what if you have, that's in row. In the column engine, we use a hash table to do the aggregation. So for each C0 value, we'll have a set of entry points in the hash table, which gives you an idea of how many distinct values are there in C1. Now, if you have an extremely high number of distinct values in C1, let's say 500 million distinct values, and C0 is a very low cardinality column. So you're doing group by store, and you have only 10 stores in your table. But for each of those stores, we have to keep a large hash table for the C1 values for each of those stores. So it could be a heavy memory usage to do that aggregation in column store. So what we can do is what we call an eager aggregation for distinct, where we convert this select count distinct into two aggregations. One is we aggregate on C0, C1, and then we do a count on and group by C0. So this is a semantically equivalent form of the query, but it uses much less memory, and more importantly, we don't have to move data in DPF. Because to do the count distinct in the earlier case, as I will show you here, we might have to move data to the coordinator, for example, to do the aggregation distinct. Or if there are 10 distinct values and you have 25 nodes, we might only make use of 10 of those nodes by sending the C0 each group to a different partition and then doing the aggregation. Essentially, there's a lot of data movement required for that to be done. Instead, we split it up into two group bys, a group by C0, C1, and a count star. And here you can see this group by in DPF is done as a partial final group by, and much of the aggregation is done here. So from 500 million, we've reduced it to 250 million. So we have much less data to TQ compared to that scenario. And a lot less memory used here. Okay. So what about if you have multiple count distincts? Again, this is something that we have in DB2, but it's a cost-based rewrite, and sometimes it doesn't take effect, and you might see that there's a lot of memory used, and we've also seen customers getting a 955 error, which is an out-of-memory error. So a way to rewrite this is to do the same thing that I mentioned in the earlier scenario, except that you do each count distinct separately. And in this case, I did a join on the group by column. So it's very similar to that previous scenario, except that we do each count distinct in a separate subquery. Okay, so you have the slides. Don't worry if the query looks complex. If you have your application developers who are writing these queries, they should be able to get this transformation if needed. Okay, so here, this is not a DPF system, but the count distinct does use a lot of memory, especially when you have a large number of distinct values in C1 and C2. In this case, the rewrite splits it up into two group bys for each count distinct. So we have group by and the count C1, a group by and the count C2. This uses a lot less memory, and then just stitch them together to get the final solution. Okay. So let's move to a different scenario. This is correlated subqueries. What are correlated subqueries? If you've written a C program and you have a loop where you're iterating and calling a function within the loop, typically for each iteration you call the function and you pass some parameters to it. So one by one you'll execute that function, come back, go to the next iteration. This is a very similar concept to the correlated subquery. You have a main query block dealing with T1, and you want to get all the rows in T1 which have the latest date. This is a version table, so you have a copy of the row for different versions. So you want to get the latest version. So typically you write it as a subquery with an aggregation function and a correlated predicate. So for each value of emp ID in T1, we call this subquery, pass in that value, do the aggregation, and give the result back. It's a row-by-row process, and it's very, very expensive. So in this case, what we do is we decorrelate the query by computing the min for the entire table for all the emp IDs, and then do this as a join. So it's this is something that we do handle in Db2 today, but I'm just illustrating what a correlated subquery is and how you can decorrelate it. There are instances which we don't decorrelate today, and the reason being that in row store, we weren't too worried about correlated columns, simply because we could always put an index and execute that subquery very efficiently, because we're just going to those rows. In the column engine, we don't have indexes typically on tables, and for each invocation of the subquery, we're going to scan the entire table. So these queries could take forever. So you have to be careful with correlated subqueries. So we're going through and adding a lot more decorrelation concepts within Db2 to avoid correlated subqueries in the column engine. So you can see here, we have 100 scans required if there are 100 outer rows, and this is going to take a long time. In this case, we do the complete aggregation with one scan and then do the join. So it's much more efficient. Okay. So this is one similar concept, except that correlated subquery is in the select list. So you have the select list here, and one of the things that we want is the max C2 from the join of these two tables, and the correlation comes from T1, which is from the main query. So once you process the main query, when you're trying to fill in the select list values, you pass in T1, C1 into that subquery, compute the max, and then put that into the select list. What we want, how we decorrelate here is to make this a left outer join on the subquery, and put the correlated predicate on the outside of this left outer join. So we know that a left outer join, in this case on C1, it's unique, so it's not going to change the output. You're going to get one row out. If this is an empty set, this will be a null value. Okay, so this is correlated subquery converted into an outer join, and a lot more efficient. Again, because we don't need to scan the table 100 times, we do the aggregation once, and do the left outer join and fill in the select list value. Sure.
Which query optimization does this
So, sorry?
Which query optimization?
So these are not automatic rewrites at the moment. This is something that you might want to rewrite manually. If you do see a case like this, we do convert it automatically for all optimization levels.
Yeah, but I have tried some reduction techniques in the past. The default optimization level, it goes back to the same, like it rewrites the query, goes back to the same.
So you have a similar situation? Yeah. I'd like to see that scenario if you can. Yeah, whenever you can send me. My email is at the back of the slide. But yeah, there are some cases where we don't do this rewrite, and you might want to do it manually if that is the case. Again, this is one that we are focusing on to do automatically for most scenarios. With OR predicates, I just have OR predicates left. This is OR join predicates. So if you have a complex predicate like this, a join predicate involving T1, T2 with an OR predicate, we cannot do a hash join. Hash join is solely reliant on equality predicates. If you have a complex predicate, we have to do a nested loop join. And a nested loop join essentially, when it involves columns from both sides of the table, it's almost like doing a Cartesian join and applying the predicate. So it's very expensive. And here what we do is we split the query and do a union of each subterm of the OR predicate. So the first subterm is here, the second subterm is here. And this can be done as a hash join much more efficiently. Semantically, we require the distinct there. Okay. So you can see that a nested loop join is very expensive. We can do a hash join for both branches of the union, and that's much more efficient. So this is one with exists or exists. So it's very similar to the previous case where we have an OR predicate, but it also applies to not exists and not exists. In this case, we can rewrite it into a left outer join, because a left outer join conceptually is, give me the rows that match, and if it doesn't match, give me a null value. So just looking at whether that value is null or not, we can tell whether it matches or not. So that's essentially not exists and exists. So we can rewrite it into an outer join and test for the join predicate values as being null. If it is null, it doesn't exist. If it is not null, it exists. Okay. So this diagram is pretty self-explanatory. Doing the predicate as a correlated predicate is very expensive. So you can do it as two left outer joins and then apply the filter is null or is not null. And you can also write an OR to a union. In this case, you have the subterm, the first subterm here and the second subterm here, and we automatically decorrelate this. So there are different ways of writing an OR predicate, either OR to left outer join or to union. Okay, so this diagram, it looks very similar to the previous case as well. Okay.
Question: is it more efficient to use that not exists rather than not in, or do they work the same?
So that's a very, very good question, because a lot of people do not understand the semantic difference between not in and not exists. There is a difference. A not exists, a not in predicate in the presence of nulls gives completely different results than a not exists predicate. So internally in Db2, we convert a not exists into an anti-join. An anti-join is exactly like a left outer join, but instead of finding the matches, we say throw the matches away and give me only the null values from that side. In fact, I don't even need the null value. I just flow the row, so it doesn't exist. A not in, when you have nulls, the result is null. So you have to be careful. If it is a not null column, the results could be different if you have nulls in it. So it's not a question of is it better to write it as a not exist, but is it the semantics that you want? So typically, if you don't have nulls, use a not exist. If you have nulls in those columns which you're testing, you have to use a not in, because the results will be different if you want that semantic. If you use a not exist, it'll behave like it'll ignore those nulls. Okay. So to summarize, we do have a very, very powerful rewrite engine. It's extremely powerful. We have lots of techniques to do rewrites in there. We do have cost-based rewrites, but it may not be perfect. If you run into a problem, what I've given here is a set of interesting rewrites, and I think covering a lot of the common rewrites that we see, techniques that you can use, but these are techniques that we will also be putting into DB2. Okay, thank you.
Thank you.